Hi everyone, my name is Corey Macdonald. I'm a robotics research engineer with Astrobotic, and today I'm going to be representing the team talking about the validation of photometrically corrected lunar images. Photometrically corrected lunar images are important to us in the context of terrain relative navigation. So Astrobotic is currently developing our OPAL system, or Optical Precision Autonomous Landing, which is a commercial bolt-on terrain relative navigation sensor system to enable 100-meter precision planetary landing. This system has been developed in partnership with JPL, NASA JSC, and MOOG, and the sensor is going to be demonstrated on Astrobotic's lunar missions in 2021 and 2023. So what we're looking at in the lower left-hand side is a flight test of Astrobotic's terrain relative navigation system, as well as hazard detection several years back aboard a Maston Zombie. And then on the right-hand side, you can see a visual of the accuracy that we're able to achieve without terrain relative navigation relative to the accuracy that we're able to achieve with terrain relative navigation, which represents an about 100x improvement. Just to provide a little bit of context about OPAL TRN's concept of operations. So OPAL TRN operates during lunar descent from approximately 15 kilometers altitude, and features and descriptors are extracted from camera image data that's coming in at about 1 Hertz. This data is compared to onboard map data, which is what we're really interested in here, and matches are determined and outliers are rejected, and the correspondences between the landmarks of image and map data are then used to calculate pose estimates. In order to generate maps for OPAL terrain relative navigation, we generate digital elevation models from orbital datasets using state-of-the-art photogrammetric methods. In addition to this, we remove shadows from these orbital data sets and specifically images to enable re-rendering to the illumination conditions that we anticipate seeing on mission. And in addition to this, we perform robust verification and validation on the resulting data to account for geodetic alignments, distortions, ephemeris accuracies, and elevation accuracy. So on the right-hand side here is a quick demonstration of Lunar. Lunar is our physics-based ray tracing engine built from the ground up for terrain relative navigation applications. It uses the Vulkan API and NVIDIA's RTX real-time ray tracing capabilities in order to simulate the solar illumination onto the terrain at any specific date and time using spice-based ephemerides. And so we use Lunar in order to render the terrain to produce simulation data for software and hardware in the loop testing, as well as for producing mission data that we compare the incoming images during descent to. Photometrically correcting lunar images is a key step towards developing maps for terrain relative navigation, because the shading from the orbital images that we're using needs to be removed in order to ensure an artifactless rendering to make sure that the illumination conditions are true to the time of the mission. In the lower left-hand corner, we're looking at a publicly available Chang'e 4 descent image, and on the right-hand side, we're looking at a Lunar rendered reference image, which has been rendered to the same date and time as the Chang'e 4 descent in order to reproduce the illumination conditions at that time. You can see here that our feature matching algorithm is able to accurately identify a number of correspondences based on these terrain features, which is an important first step in order to be able to produce an accurate pose estimate. On the right-hand side, you can see that we're comparing Lunar renderings to an LRO wide-angle camera image. And so on the left-hand side, the LRO image and Lunar render match in terms of illumination conditions very well. But then along the right-hand side, you can see that as we vary the timestamp on these images, you can see how the illumination conditions vary and remain true to the date and time that we are looking at. So to dive a little more into the photometric normalization process, so photometric normalization is used to extract surface features from the illumination effects induced by topography from satellite images. Photometric models capture the dependence of reflectance on the locally calculated incidence, emission, and phase angles, as well as on the particular scattering properties of the surface material. 3 photometric models are considered in this work: Lambert, Lunar Lambert, and Hapke. Lambertian reflectance is based on the observation that the surface brightness is dependent on the incidence angle and is independent of the angles at which the surface is viewed. The Lunar Lambert model accounts for the dependence on viewing angle by employing the Lommel-Seliger function at small phase angles and Lambert's cosine law at large phase angles. This describes the multiple scattering among soil particles and macroscopic roughness more accurately than the Lommel-Seliger function alone. The spatial variation in the composition and maturity of the lunar regolith is accounted for by the Hapke model, which provides a set of empirically derived parameters to account for the physical properties of the lunar regolith. Each of these models is applied to the locally calculated phase incidence and emission angles to adjust the pixel brightness to a normalized viewing angle. On the right-hand side here, we can see a sample NAC image, as well as its photometrically corrected image in B, as well as the incidence and emission angles. Validation of the photometrically corrected data is critical to ensuring that 1. The dependence of reflectance on the angle of incidence is removed, and 2. That shading artifacts are corrected such that data can be rendered to a target date and time of interest. To address the second point, the photometrically corrected images are rendered and compared to the illumination conditions of an independent target LRO narrow angle camera image. This rendering is done using Lunar. Renderings are compared to target NAC images via the structural similarity index, as well as a pixel-wise root mean square error. Results here are presented for 2 regions. In the Lacus Mortis Plateau, southwest of Berg Crater, which is near the landing site for Astrobotic's Peregrine Mission 1. A wide range of geometric angles highlights the variations in the chosen photometric models. Therefore, a second, more topographically varied area was chosen in the Highland Ponds region. For the Lacus Mortis region, an internally generated and validated DEM at approximately 4 meters per pixel was used. For the Highland Ponds region, a publicly available terrain model was used at about 5 meters per pixel. A sample of photometrically corrected data rendered to the illumination conditions of an independent image in the Highland Ponds region is seen on the left-hand side, showing the results for the Lambert model correction, Lunar Lambert model correction, and Hapke model correction relative to the original target NAC image. The right-hand side, Table 3, summarizes these results, showing the structural similarity index measure, SSIM, as well as the average pixelized root mean square error, or MSE, for the Lacus Mortis, LM, and Highland Ponds, HP regions. The structural similarity index measure was calculated to provide a similarity measure that accounts for luminance, contrast, and the structure of either image, whereas the root mean square error is calculated to show the average pixelized difference between the reference and rendered images. As can be seen here, the Hapke model consistently produces the highest SSIM and the lowest RMSE results, which correlates in both metrics to being the best results. Table 2 shows the derived slopes between the reflectance and incidence angles. So the dependence of reflectance on incidence angles can be understood by deriving the slopes of the line of best fit from the resulting data. Photometric correction effectively removes this coupling, as can be seen in this table. Here we'd like to show just a few more results of some data products that are the culmination of many photometrically corrected NAC or Kaguya images. These large areas of photometrically corrected data provide us more flexibility in terms of simulation, software and hardware in the loop testing, and production of mission data by enabling more variety in viewing positions and illumination conditions. On the left-hand side, we can see the reference NAC or Kaguya images that the photometric corrections are performed on. On the right-hand side, we can see that the shading artifacts produced by the specific illumination conditions of the spacecraft at the time of image capture are effectively removed. The red boxes represent the approximate area of coverage of the data products. This work summarizes the motivation for and the validation efforts of photometrically corrected lunar images, progressing toward being able to use this data for future missions using TRN. In this work, we found that the Habke model consistently achieves the best results, and along with the Lunar Lambert model, demonstrates a large increase in performance relative to the Lambert model alone. The Habke model, however, is more complex than the Lunar Lambert model, requiring the use of spatially varying parameters and more complex equations, which impacts computation time. In practice, the trade-off between complexity and output performance must be made. In addition to this, further work is required to derive the dependence of rendering accuracy on the variation in input image illumination conditions. If you have any questions on this work, please feel free to reach me via my email listed below, and I look forward to meeting everyone at the workshop. Thank you.